I've titled this little episode Differential Equations 4a because it continues on from the previous episode on differential equations, which was number 4. And this one is primarily for science candidates. And it deals with the energy stored in a capacitor. And we get to the answers here by application of the first order linear differential equations covered in the previous episode. In other words, differential equations number 4. Now, it's assumed that you know that, first of all, by definition, Q, the charge in a capacitor, is equal to the capacitance times the voltage. That is the definition of capacitance. It is the ratio of charge to voltage. Q standing for charge and V, of course, for voltage. And also that the electric current, I, can be represented in differential calculus form as the rate of change of charge with respect to time, in other words, dq dt. And also that energy is V times I times T, or I squared R times T. So I'm assuming that you're familiar with those formulae. Now here I've drawn an elementary circuit of a capacitor. There's always some resistance in a circuit, and I've modeled that as a single resistance R. Now, using basic Kirchhoff's law, we know that E, the applied EMF, will equal the voltage across the capacitor plus the voltage drop across the resistor, which are represented by V and by I times R. And V, by the definition given above, is Q divided by C, and IR is R times dQ by dt. I'll repeat that again. V plus IR equals Q over C plus R dQ dt. That's by definitions given at the beginning. And moving this around, the formula, we can put it into the form dq dt plus Q over RC equals E over R. All I've done there is divided through by R. Now you may recognize this from the previous episode as a linear differential equation of the first order. The integrating factor is E to the integral of 1 over RC dt. So, let's take that. Just making a correction so I can get the eraser to work, which appears to be not the case at the moment. Okay, so carry on from where we were before. The integral, when we work it out, is just E to the power T divided by RC. And then, using the methods we did in the previous episode, Q times the integrating factor, E to the power T over RC, is E over R, integral of 0 to T, E to the T over RC dt. The limits being the start of the time, which is 0, and T, the time at any instant. And that easily works out to E over R, E to the power T over RC divided by 1 over RC, which equals CE, E to the T over RC between the limits T and 0, which comes down to CE, right down to here now, it comes down to CE e to the power t over rc minus 1. And so multiplying both sides of that equation by e to the minus t over rc, we get q equal to ce bracket 1 minus e to the power of minus t over rc. So we're down to here. So we've got an expression for the charge q. Right. Notice that when t tends to infinity, the exponential term disappears and we get q equals ce or cv, because when it's fully charged, e and v will be equal. Next, we're going to use the fact that I equals dq dt. So I'm differentiating this expression here, and we get ce equals ce bracket 0 plus 1 over rc e to the minus t over rc, close brackets, which works out to this expression here. All right, that is just a bit of simple algebra. There shouldn't be a problem with that bit. Now we can see that that will tend to 0 when t tends to infinity. And notice also that when t tends to infinity, v and e are the same. I'll keep stressing that. Okay. Now, finally, the energy supplied to the system will be given by this formula here. That's E times I, but E is constant, so we can take it outside the integral sign. I is e to the minus t over rc times e over r. So that gives us this expression here. And carrying out the integration, we get down to e squared over r, e to the minus t over rc over 1 over rc. So we're down to here. And between the limits 0 and infinity. We've changed the order of the limits because of the minus sign that would arise in the integration. And that simply comes down to e squared c, or cv squared, as v and c are equal at full charge. However, some of that energy is lost to the resistance, and that is given by I squared r dt. Okay, basic formula. And so that then you can take the r outside and some of the other terms, the constant terms outside, e squared over r squared times r integral between 0 and infinity, e to the minus 2t over rc dt. Because remember, we're squaring the I there. That's where the 2 comes from. And working out that integral, we get e squared over r, e to the minus 2t over rc, all divided by 2 divided by rc. And again, we've switched the order of the limits because of the minus sign arising in the integration. And that comes down to half ce squared, or half cv squared at full charge. So the total energy supplied to the capacitor is the total energy supplied to the system, which is this, minus the energy lost to the resistor, which is that, which is half cv squared. Now that might seem a little bit long, but it is, I believe, much more logical than some of the stuff that I've seen in various books, where the explanations have been tantamount to smoke and mirrors. I'm not going to mention any specific books in particular, but I dare say you've come across them yourself. Well, thank you for listening, and thank you.